this
Session.
momentum problem with impulse. Okay, so let's start off with oh, that's a good question. So a car is traveling, if there's two L's in there, at yeah, sure, why not? 10 meters per second, and then 30 meters per second. So that'd be its velocity vector. So 10, 30. When it hits is great. Hits and bounces perfectly off of a wall. How much of the force vector did the wall experience?
What's that first part of information there?
It says a car is traveling.
And then the
First line. And
yeah,
then
second.
it says 10 meters per second in the X, 30 meters per second in the Y, for the velocity.
Okay.
I think if I get out of the picture, it comes into focus better. Yeah,
Nope.
not so much. Nope. Okay. So to visualize this, what we have happening is, let's see, that's plus X direction, plus Y direction. So I'm having the car, that's the velocity of the car.
So you said it bounces perfectly. That means there's no momentum lost to like the car being crushed or anything.
Drive.
Yeah, right. There's bouncing perfectly is the key word for this is going to be an elastic collision. So we could use energy if we needed to across the equation. We won't in this case. But it also means I don't have to worry about any energy loss to the wall.
Okay.
Okay. So let's see. So it'll ricochet like that. Off the wall. So if I was doing this better. I was Take that away. And then put it down here someplace. Whee. So that when asked about the two questions, about the two pictures rather, I clearly have the initial and the final two pictures.
We need mass for this.
Are we gonna cancel out?
We're going to need mass and we're going to need an impact time. So let's add those while we're thinking about them. So
Do you always need the impact time for these?
again, it's one of those things that's going to point you towards impulse instead of energy.
Okay.
So the car mass we'll put at, easy to divide, 140 kilograms. And the time for the collision, 0.001. We'll make it this way, 007 seconds. This is a fairly typical impact time, something down in the millisecond range. We doing okay?
Yep.
Yeah.
All right. So what we'd do is we'd say, if you guys hadn't asked me for a impulse momentum question, we'd look it up. So is there a collision? Yes, we have a collision. Let me actually get my chart. Is it rotating? No, thank God. Is there a time dependency? Yes, I have a time. So that means I have to use conservation of momentum with impulse. So we're driven to delta P equals integral F dt. Forces vector here. So let's take a moment then and define what perfectly means. Perfectly for us means that the magnitude of the velocity initial is the same as the velocity final. And yeah, let's just work that out and see what happens. So delta P, our system, it's just the car. And I have that external force. So let's with all this set up, we can now dive into the approach section. And in the approach section, we make a decision. Do we want to do the system and the momentum, or do we want to do the external force and the impulse? Yeah, they both have to get done, so it's just a matter of when. So for the approach, what we're going to do then is say that our impulse is just equal to integral of f dot dt. I did not say dot there. This said multiplied by. Okay. Because time's not a vector, this approach breaks itself up. So I'm going to have the impulse in the x direction equal the force of x and our time. And I'm going to have the impulse in the y direction, integral force component in the y direction dt. So at this moment, we're stuck insofar as I don't know the force. All I know is the time. I'm trying to find the force, but I'm not given the time. So we climb into our next approach, which is the other side of the equation. And we're going to get here that delta P as a vector. Let's analyze this for a moment. This is going to equal P final as a vector minus P initial as a vector, which means, oops, I'm doing my approach in green, which means that I need to do momentum in the x direction. In fact, let's just do the change in momentum in the x direction. And that's going to equal the mass of the car, its final in the x direction, x final, minus the mass of the car x initial. There you go. So we look at our velocity, the 10 meters per second, 30 meters per second. We look at our chart and we see that we come in, sorry, the x direction would go in this way, and the x component would go out this way. So that would be Vx. And that would be Vx in that picture. It's a perfect, go ahead.
Should our x final be negative?
That's what I'm getting to, exactly. So we're going to wind up with the mass of the car, the velocity in the x direction, minus the velocity in the x direction. So we'll just get, let me work upwards, -2 mass of the car, velocity in the x direction initial. Then if we come down here and do delta P y, we get the same thing, mass velocity in the y direction final, mass times velocity in the y direction initial. We come up here and we're going to notice that pushing up is our Vx in both of these pictures. And I meant to say Vy in both of those pictures. So since the velocity initial and the velocity final have the same value, in the y direction, the change momentum in the y direction is 0.
How do we know the same value?
Because we're looking at the components of the velocity, and initially it's coming up, so it's going to have an upward pointing velocity in the y direction. And in the final picture, as the car bounces this way, it still has that velocity y going upward. So the sign plus or minus of the velocity in the y direction never changes. In Vx, we went in, we hit the wall initially, and in the final rebound state, Vx is now going the opposite direction. So we absolutely have a change in momentum in the x direction. Which we just saw was -2 times the mass of the car and the initial speed of the car. But notice what the 0 in the y direction does for us too. It comes over here and says, I can't have an impulse in the y direction. If there's no force in that direction, I'm sorry, if there's no change in momentum in that direction, I don't get a change from the impulse. So I don't have to worry about this term at all. Okay. So let's take the little space right here. And okay, let's plug in numbers and equations and see what happens. So we know -2, the mass was 140. Kilograms. Our velocity in the x direction was 10 meters per second. And that all has to equal F and our delta T, 0.007 seconds. And yeah, we can crunch the math and get some answer out of this. You guys crunch the math yet?
Negative 19.6.
Negative 19.6. Oops. And let's see, units ought to be kilograms, meters over second squared. And kilogram meters over second squared is just force. So when we go up to these pictures, that means we're getting a force from the wall this way, perfectly in the negative x direction.
So then that's the same force going in, right?
Well, it'd be that, yeah, initial and final. During this entire time interval for the collision, we have this force, which we'll just assume it's constant, or we can assume it's an average force during that time interval. And that's the force from the wall on the car.
Isn't that just the force from the x direction though?
Yeah, yeah, absolutely.
And
that
didn't it
force
come in at
caused-
an angle?
It did. And it left at an angle with the same velocity.
I see.
So the only thing that really changed was 10 meters per second initial in the x direction became negative 10 meters per second in the final case.
And then we didn't actually have to integrate because there
Nope.
wasn't a time dependency on the force, right?
Correct. The fact that we had the delta t, a time interval already defined, said that we can just skip the integration and write it as f dt.
Got it.
Well, f delta t rather. All right, so here comes the subtlety that I would be much more clear when I wrote to the problem statement. But the car is traveling, it hits and bounces off of a wall. How much force did the wall experience? Everything here has been the system of the car. So the force we drew is the force the car experienced from the wall. With me so far?
Yeah.
Everything we've been done is with the car. So if I get curious about the wall, it's going to be the third law pair and go in the opposite direction. So that would be F wall. Which is right along my light spots.
So then it would be a positive force.
It'd be the same numerical value, only positive in direction. So our 19 points, it would be, the force from the wall would be 19.6. So to really answer the question completely, you got to take it in the wall's point of view. And it feels something smacking it this way.